In some situations subsurface inequality may not be that sharp. Let us try to look at that example. Let x be a random variable with PDF given by this. So 1 by 2 root 3 if x lies between minus root 3 to root 3, 0 otherwise. Let us look at mu is equal to expected value of x. So that means I have to integrate x with the PDF. So x with PDF 1 by 2 root 3, it has been integrated over the support which is minus root 3 to root 3. It is a odd function, range is from minus a to a type, so this would be 0. Let us look at sigma square which is equal to x square. So I have to integrate x square with the PDF. So the range over which I have to integrate is minus root 3 to root 3 x square. Then the PDF is 1 by 2 root 3 in this range. Work it out, this turns out to be 1. So sigma square which is same as x square because mean is 0, this turns out to be 1. So I apply the subsurface inequality for epsilon is equal to 3 by 2 which gives me probability mod of x minus mu, mu is 0 is greater than epsilon sigma. Since sigma is 1, so that is the same as probability mod of x is greater than epsilon which is 3 by 2. This would be less than or equal to 1 upon epsilon square. 1 upon epsilon square is 4 by 9 which turns out to be 0.444 approximately. So in this case subsurface inequality gives me this. Now let us try to calculate this probability exactly. So probability mod x greater than 3 by 2 is same as 1 minus probability mod of x less than or equal to 3 by 2. But probability mod x less than or equal to 3 by 2 is same as x lies between minus 3 by 2 to 3 by 2. So if you have to find the probability of this, you have to integrate the PDF over this range. Your PDF is minus root 3 to root 3, it is 2 by root 3. And this minus 3 by 2 to 3 by 2 interval is contained in minus 3 by 2 to 3 by 2 is contained in minus root 3 to root 3. So that is why you integrate it over here. The PDF is in this range is 1 by 2 root 3 dx, and if you calculate is 0.134, which is smaller than the value which we got using the subsurface inequality, which is 0.444. So this is less than or equal to 0.444. This is the one which we got using subsurface inequality. So these are subsurface bound. Now let us talk about some inequalities about expected value of a function of a random variable. Before we do that, let me introduce the concept of a concave functions and a convex functions. So let minus infinity less than a less than b less than or equal to infinity, a function phi from the interval ab to r is said to be convex or concave on ab if phi alpha x plus 1 minus alpha y is less than or equal to alpha phi x plus 1 minus alpha phi y in case of convex function, and this inequality would be greater than or equal to this quantity in case of a concave function. Now I will say that my function is strictly convex or strictly concave if the inequality over here is strict. That means I have a strict less than or strict greater than. Let us try to interpret this condition. What is alpha x plus 1 minus alpha y? It is a mean of x and y. So it is some point between x and y. So I am trying to look at, suppose x is over here, y is over here. So this point would be alpha x plus 1 minus alpha y, some point in between. I am saying value of the function at this point is always less than or equal to the value. So suppose phi x was here and phi y was here. So 1 minus alpha times phi x plus 1 minus alpha phi y would be over here. So I am saying the value of the function here should be less than or equal to this thing over here. So that means this is like this. So this is the value of the function over here, and alpha phi x plus 1 minus alpha phi y. Basically, if you vary alpha, this would be this card. If you vary alpha, it will be this card. For example, alpha is equal to 1, it would be x. Alpha is equal to 0, it would be y. It would just go over here. So as you vary alpha, you get points over here. So I am saying that this point is always less than or equal to this thing. Or equivalently, what it suggests is a function phi is convex if the chord joining any 2 points on the curve is always above the curve. And in case of a concave function, it happens other way. That means chord joining any 2 points on the curve would always be below the curve. So that means concave would look like this. So the chord joining any 2 points is always below the curve. Let us try to see how you can check whether a given function is convex or not. That is normally very simple. So let phi is a function from AB to R. Then clearly phi is convex if and only if minus phi is concave, because less than inequality would get converted into greater than or equal to if I replace phi by minus phi. So phi is convex if and only if minus phi is concave. Now checking convexity or concavity becomes very easy if I know that my function is differentiable. So let phi be differentiable on AB and let phi prime denote the derivative function. Then phi is convex if and only if phi prime is increasing, and it would be concave if and only if phi prime is decreasing. So that means to check whether a function phi is concave or convex, just check whether derivative is decreasing or increasing. In case of convex, the derivative has to increase. In case of concave, derivative has to decrease. Convex, it has to increase. So of course then C is a easy consequence of B. Phi is twice differentiable, then and let phi prime denote the second derivative function. Then phi is convex if and only phi prime is increasing. Phi prime is increasing, that means derivative of phi prime is greater than or equal to 0. So which is equivalent to saying that phi double prime is greater than or equal to 0. And in case of concave function, it would be concave if and only if phi double prime x is less than or equal to 0. So note that if you know that your function is differentiable or it is twice differentiable, then checking convexity becomes very simple. Just look at the first derivative or the second derivative and the convexity can be checked in a straightforward manner. Now let us do this famous Jensen's inequality. This is one of the very useful inequalities, and we will see that we get many results from this Jensen inequality. So let x be a random variable, and suppose its support is contained in an interval AB, and phi is supposed a function from AB to R which is convex or concave. Then expected value of phi x would be greater than or equal to phi of expected value of x if phi is convex. If it is concave, then expected value of phi of x would be less than or equal to phi of expected value of x, provided the expectations exist. So I will prove the result for a case where phi is differentiable. So for simplicity, assume that phi is differentiable on AB. Then I know that phi prime is increasing on AB for x belonging to Sx. Now note that my support is contained in AB, so that is my PDF has to be integrated over AB along with x to get a mean. So that means my mean mu, which would be nothing but I can write down A to B x fxx dx. This would always be between A and B, because I know that my probability that x lies between A to B is 1. Then we saw that if probability that x lies between A to B is 1, then the mean has to be between A to B. So that means my mean has to be between A to B. So I apply the mean value theorem or the Taylor series expansion of phi. So phi x becomes phi of mu plus x minus mu phi prime xi for some xi between x and mu. Now note that in the case of convex function, phi prime is increasing. Let us consider two different situations. Suppose x is greater than mu and xi is between x and mu. Now in this case, I know that in this case x is less than mu, so phi of xi, because phi is increasing, so phi of xi would be less than or equal to phi of mu. But in this case, x minus mu is a negative quantity. So if I multiply x minus mu both the sides, the inequality gets changed. So x minus mu, this is a phi prime. Phi prime is increasing. So phi prime xi is greater than or equal to x minus mu phi prime. Now let us consider the case 2 where mu is less than x. So xi is over here. In this case, phi of xi would be greater than or equal to phi prime xi would be greater than or equal to phi prime mu, because phi prime is increasing. But in this case, x minus mu is positive, so if I multiply x minus mu both the sides, the inequality doesn't change. So x minus mu phi prime xi is greater than or equal to x minus mu phi prime mu. So whatever may be the position of x and mu, whether x less than mu or x greater than mu, x minus mu phi prime xi is always greater than or equal to x minus mu phi prime mu. And that is what I put over here. So this says phi x plus is greater than or equal to phi mu plus x minus mu phi prime mu for all x belonging to AB. Actually this equation has very intuitive justification. What is this quantity? This is a tangent to curve y is equal to phi x at the point mu phi mu. So what it is saying, if you look at the curve is always above the tangent at any of its point. So that means it is like this, the tangent would be here and the curve is always above this. So that is what happens for the convex function. Concave, it would happen the other way. So phi x is always greater than or equal to phi mu plus x minus mu phi prime mu. I replace this x by capital X for all x belonging to AB, since probability x belonging to AB is 1. So I replace small x by capital X, which is a random variable. So phi x would be greater than or equal to phi mu plus x minus mu phi prime mu. Now we know that if x1 is greater than or equal to x2 with probability 1, then expected value of x1 is greater than or equal to expected value of x2. That also we know. If probability of this is 1, then so I apply this because this quantity is greater than or equal to this with probability 1. So expected value of phi x would be greater than or equal to expected value of this quantity, but phi mu is constant. So phi mu plus expected value of this. So phi prime mu is constant, which goes outside, and so this becomes just 0 because this goes outside and expected value of x minus mu is 0. Sorry, so this would be equal to, that was okay. So expected value of phi x is greater than or equal to phi of mu, but mu is same as expected value of x, so which is same as phi of expected value of x. So in case of concavity, the equality would be reversed. So let us consider some examples. So what I have proved is phi convex implies that expected value of phi x is greater than or equal to phi times expected value of x. Let us look at phi x equal to mod x. Mod x graph looks like this. So this is clearly convex. This is convex, so expected value of phi of x, which is equal to mod of x, would be greater than or equal to phi of expected value of x, which is same as mod of expected value of x. Let us consider phi x equal to x square. The double derivative here is 2, which is always greater than 0. So phi is convex. So expected value of phi x would be greater than or equal to phi of expected value of x, and you get this inequality. Similarly, let us look at the function phi x equal to x to the power r, where r is greater than 1 and x is in 0 to infinity. If x is in 0 to infinity, that is the reason why I am taking probability x greater than or equal to 0 to be 1. So if I look at double derivative over here, that turns out to be r into r minus 1 x to the power r minus 2, which is greater than 0 for all x greater than or equal to 0, provided r is greater than 1. So that means this function is convex. So expected value of phi x would be greater than or equal to phi of expected value of x, which is same as expected value of x to the power r would be greater than or equal to expected value of x whole power r. Same example, let us now take r to be less than 1. If r is less than 1, this quantity is negative, x is positive, so this quantity would be less than or equal to 0. So this becomes concave function. If concave function is there, then inequality gets reversed. So r less than 1, then inequality would be the other way. Now let us consider phi x equal to log x, where x is greater than 0. So if I look at the double derivative of this, this becomes minus 1 upon x square, which is a concave function. So expected value of phi x would be less than or equal to phi of expected value of x, which gives me this inequality. Now for this case, let us look at phi x equal to e to the power x. Phi double prime x is same as e to the power x, which is always greater than or equal to 0. So here also phi is convex, so expected value of phi x would be greater than or equal to phi of expected value of x, and you get this inequality. So these were nice applications of Jensen's inequality. So now let us consider this example, which again gives us a very nice inequality. So suppose p is less than q and p is positive. Then one can show that expected value of mod of x p to power 1 by p would be less than or equal to expected value of mod of x to power q to power 1 by q. You see, we have seen in the last example that if r is greater than 1, then phi x equal to x to power r is convex. So using that we got expected value of x to power r is greater than or equal to expected value of x to power whole r, provided probability that x is greater than or equal to 0 is 1. So here in place of x I take mod of y, which is satisfying this inequality. Now note that here q by p is always bigger than 1. So I apply this on mod of y with r as q by p. So expected value of mod of y to power q by p would be greater than or equal to expected value mod of y whole power q by p. Now what I do is in place of y I take x to power p. If I take y is equal to x to power p, so it becomes x to power qp by p. So pp gets cancelled, so it becomes a mod of x to power q. Is greater than or equal to y I have taken as x to power p, so it becomes expected value of mod of x to power p to power q by p. Now I take power 1 by q both the sides, the inequality doesn't change. This would be same as mod of x to power q, 1 by q is greater than or equal to x mod of x to power p to power 1 by p, which is same as this inequality. Now one interesting observation which we can get from this inequality is if this quantity is finite, so that means if expected value of mod of x to power q is finite, then this quantity would also be finite, which is equivalent to saying that expected value of mod of x to power p is finite. So what it suggests is, because q was bigger than p, so it suggests that if you have absolute movement of higher order as a finite quantity, then the absolute movement of lower order would also be a finite quantity. So now let me give a few take-home problems which are easy consequences of Jensen's inequality. So suppose probability that x greater than 0 is 1. Try to show that expected value of x into expected value of 1 by x is always greater than or equal to 1. So you can use it, prove it using Jensen's inequality. Now let omega i's are positive constant, ai's are positive constants, and summation wi is 1. So that summation I is equal to 1 to n, ai wi is greater than or equal to product I is equal to 1 to n, ai to power wi is greater than or equal to 1 upon summation I is equal to 1 to n wi ai. Now this is called the arithmetic mean because it is a weighted mean of ai's with weights as wi. This quantity is called geometric mean, and this quantity is called harmonic mean. Now this inequality is famously known as AM, GM, HM inequality. So what it says is arithmetic mean is always greater than or equal to geometric mean, is always greater than or equal to harmonic mean. So these are the two take-home problems which are easy consequences of Jensen's inequality. Now before I conclude, let me give a summary of the things I will be doing in the next module. In the next module, we'll introduce a set of numerical measures that provide a summary of prominent features of probability distribution. You see, a probability distribution has a lot of information available. So I will look at the important information which a probability distribution carries, which would be in terms of a few numerical measures. So I'll introduce a few numerical measures which will provide a summary of prominent features of probability distribution. So that was all for this module. Thanks for your patience and have a great day.